This video is a little preview of the upcoming video called Journey to the Center of the Earth. This is material from Unit 4C, so here are the learning outcomes. You should pause the video and write them down. So, seismic waves that are generated by earthquakes provide information about Earth's interior. And the study of seismic waves for this purpose is called seismic tomography. How deep can we drill into Earth's interior? Well, we haven't been able to go very far. This is a picture of the Kola super deep borehole that was drilled over a period of 19 years and only got about 7.5 miles into the crust, which in this location was about 1/3 of the way. People have also tried to drill into the Earth's crust in the oceans. The deepest ocean drill hole was drilled in 2012 by this Japanese ship called EQKE, and it reached about 1.25 miles below the seafloor in a water depth of 3.5 miles. And that's quite a feat because you have to keep the boat steady, the boat can't move, and that drill core is built using this rig. You build it downwards, and then you take a sample and you bring it all back up, and then you take out the sample, and then you go back down and reoccupy the hole and keep going. It's quite a procedure. This ship is capable of drilling 10 kilometers below the sea level and up to 7 kilometers below the seabed, which is pretty amazing. Here's a cartoon showing all the deepest places that we've been able to go. We've got the deepest natural cave in France, which is about 5,000 feet deep, which is roughly a mile. The deepest mine in South Africa, the EQKE, which I just mentioned. The deepest drilling in the seabed off of Spain. A deep well that was drilled in Oklahoma. And then the Kola borehole that I just mentioned. We just can't go further. Notice that the crust mantle boundary is down here. So why can't we drill any deeper? Well, it's just too hot. It melts the drill. Also, the pressure is intense. When you have that drill going in and then you have to pull it out to remove the material that was collected, the walls collapse back in. And so you're just kind of drilling the same spot over and over and over again at a certain point. So luckily we have earthquake waves to tell us about Earth's interior. So this cartoon is showing an earthquake that occurs, and it sends out energy in this form of waves, shaking waves, in all directions. And what we're going to do for the diagrams and what's going to be in the video you're going to see is we're going to draw these rays which are perpendicular to the wave front, but they show the direction the wave is going instead of trying to show the actual wave. It turns out seismic waves travel at different speeds in different rock types. So I know we haven't learned rock types yet, but there are 2 rocks listed here, sandstone and basalt. And sandstone is a little bit looser of a rock in terms of how well it's cemented. So seismic waves, earthquake waves, travel slower in sandstone compared to basalt. And I will draw your attention to the fact that in the video, she's going to use the term seismic velocity a lot. And so what that means is the speed of the earthquake waves. Earthquake waves will also travel more quickly in a solid than in a liquid. So here are some P waves traveling through solid, and then here they are traveling through a liquid, which you can think of as maybe the outer core being liquid and the inner core being solid. This has to do with the density of these layers. The more packed the material is, the faster the waves will go through it. And then remember that S waves cannot travel through liquids. So when we have a boundary, such as the core mantle boundary, where the outer core is liquid, P waves will continue through, but the S waves will stop. And this is a very important fact in terms of how we are able to identify that liquid outer core. So when light travels from one medium to another, it bends or refracts, such as this light that's coming in, hits some water and bends. And you might have noticed this if you've ever been standing in a shallow pool of water or you put a stick in the water. It looks like it bends funny, right? Of course, your legs are not bending funny. It's the light that's bending because the light in the water travels at a different speed than the light in the air. And the video is going to show you this as well. So these rays, when they go from one major boundary to another, are going to refract or bend. So in this case, I have a faster speed up here, so it must be more dense, a slower speed down here, so it must be less dense. It turns out the waves become more direct or perpendicular when they go from a more dense to a less dense substance. If we switch that order over here, where a less dense layer overlies a more dense layer, then the wave travels faster in the lower layer and it bends in this sense. Now, what's going on in the Earth? Well, in general, it's this diagram on the right. The deeper we go, the more dense the layers are, the more compact, the more pressure there is. So what happens overall is when there's an earthquake, these waves go down and then they bend back up. Again, that's what's going on here. It's going to bend back eventually up to the surface. Now, if we had stacks of layers of rock in the earth, then we'd have these very distinct bends in the seismic ray paths, and eventually they would reflect back to the surface and bend again. But in Earth, we tend to have more homogeneous changes in density, and so the waves make more of a curve from the earthquake location and then back to the surface of the Earth where they can be measured by a seismic station. So hopefully all of this is going to give you some background to help you understand what the video is going to be talking about. So here are some things to pay attention in the upcoming video. What are the two types of body waves generated by earthquakes? Why do S waves only travel through solids? How do we know the precise size of the core? Does the density of Earth's layers generally increase or decrease as we move from Earth's surface deeper into the Earth? That should say move, not more. What is the MOHO? And how do the speeds of earthquake waves change as they pass through various layers in the Earth? When you're done, I'd like you to try pages 37 and 38 in your lecture tutorial, and in my follow-up video, I will go through these pages with you. Time to watch Journey to the Center of the Earth.